So in this video, let me first give you a sample question for what we have done till now for series solution, and we are now solving for differential equations that do not have constant coefficients. So try solving this one: plus x y dash plus, or say, minus y equal to 0. So solve this, take up any initial conditions in the general form and try coming up with a solution for this. We already know that a naught and a1 are the free parameters. So your solution should depend on a naught and a1. So you should be able to repeat those steps and come up with an expression that justifies and that satisfies this differential equation. So today we are going to in this video we are going to look at the solution that we have already found. So the Airy's equation, y double dash minus x y equal to 0. We already solved this and saw that y of x was equal to a naught 1 plus x cube over 3 into 2 plus x 6 over 6 into 5 into 3 into 2 plus so on, and plus a1 x plus x4 over 4 into 3 plus x7 over 7 into 6 into 4 into 3 and so on. Let us say this is a function. So we can write the solution and simplify its expression by writing a naught, and let us say this is a function of x. Let us call it a y naught of x, and plus a1. Let us represent this with a function notation as well. So what we are really looking at is the nature of this y naught and y1. We are interested in finding this. So one thing you should look at is that if we have the original differential equation in such a way with initial conditions that if y of 0 is found, then x is equal to 0 is put, that we get a naught here. So if this alone, y naught of x, this alone would be the solution of this differential equation, then it would mean that y of 0 would be putting x is equal to 0, and we are going to get because this is a solution, this alone is a solution, y of 0 would be equal to 1. So all these terms with x become 0 when we put x equal to 0, and we get this 1. And if we take the derivative of this y naught of x, then this will be 0, and the first term would have x square in it. And when we put x is equal to 0, we are going to get the derivative at 0 equal to 0. So if this Airy's equation is solved with initial conditions that y of 0 is 1 and y prime of 0 is 0, we are going to get y of x is equal to y naught of x. So this is going to become the solution of the differential equation. We can check this and we can see that. Similarly, if this would be the solution, suppose this is the solution, the only solution for this differential equation, then we see that y1 of 0, putting x is equal to 0, makes it 0 because all the terms have x in it. And if we take the derivative of this, so the derivative of y1 at 0 and then put x is equal to 0, so we get 1 here and all the other terms are going to have x, so we are going to get this. So if the initial conditions in the original equation given would be y of 0 is 0 and y prime of 0 is 1, then we will get the solution to be equal to this solution. So when we are interested in the nature of a function, the y0 and y1 here, we actually are interested in looking at the graphs of it. Obviously, it is not easy to draw the graph of such a complicated series because we have large powers of x. So for any value of x, it's not easy to compute this and find the value. So we can use some online tools, for example MATLAB or some online solver, and try to plot a graph for this or solve this differential equation and get the solution. For example, the ODE 45 solver can solve it, but we are not just interested in that. I just wish to emphasize a few steps, and obviously you do not have to do this in the exam, that which whatever is very difficult to do even in normal setting will never be asked in the exam. But if one is truly learning, one is always interested to develop some insight into general solutions. So what we are interested in is finding the expression, finding the graphical representation of the Airy's functions. This is known as the Airy's equation, and these two are called Airy's functions. So we are interested in finding the graph, how we can plot y naught of x with respect to x, and how we can plot y1 of x with respect to x. So if we use some solvers, we can see that y naught of x at 0 would be 1, as we have it here, and its derivative would be 0. Derivative 0 means it would be constant at this point. So whatever the function is, it will come up to be constant or has a gradient that is horizontal or parallel to the x-axis. And then we obviously know only this point and its gradient here by this simple initial values. And we can similarly see that the y1, the Airy's function y1, would have a value of 0 at 0, and it would have a gradient of 1, so it means the slope would be 1 at this point. So if we take up these values and if we solve this using some online solver or MATLAB, for example, the exact graph of these would be something like this. This is not an exact drawing, so I am not drawing the complete scale, but we at least know this is 1. This is 1. And after 0, it will be something like this. So that's quite interesting that for positive x it has such a nature, and for negative x it has an oscillatory nature. So and for this one it is something similar. We get something like this, and so for positive x it has such nature which is not oscillatory, and for negative x it is oscillatory here as well. So that's very interesting. For positive x, both these have exponentially rising uh, graphs, but for negative x we have oscillatory behavior. So how is this possible? We can have more insight by just inspection, by looking at this expression. So look at it closely. So when x is positive, we have a second order differential equation of this form. And when x is negative, we have differential equation of this form. We have just solved it in 14.1. So the solution for this was a sine cosine based solution which is oscillatory, and I have given you the sample problem where you can very easily solve this and see that it is an exponentially it is an exponential solution. When you can solve it and try some online tool to plot it, you are going to get this. So this is just a little commentary on these Airy's functions, and also the importance of understanding or knowing the behavior of something just by inspection. If we cannot completely comprehend something, we can at least deduce or get out some observation about that thing. So by looking at these, it was very difficult to see how the graphs would be plotted. We have not done that. We have just used some, say, online tool or some computer tool to plot them. But looking at their behavior for positive values and at 0 is easy to find, and some at negative values can be comprehended by looking at the original function. So I think you guys should as sample practice problems do these or these. Take up this Airy's equation as the second order differential equation with non-constant coefficients, and then use the initial condition. In problem A, you can solve for y naught equal to 1 and y prime naught equal to 0, and prove that the solution would be the Airy's function y naught. And in the second, you can just flip the initial conditions to prove that the solution would be the Airy's function y1. So do these sample practice problems, and you would not only master the technique of series solution, but you would be one step ahead in order to solve second order differential equations with constant coefficients or without constant coefficients using series solution.